Now that we've defined current and resistance, we're going to put them together and relate them to voltage, which we learned about in the last unit. And the relationship between those three things is called Ohm's law. And Ohm's law looks like this. It is the voltage in a circuit or in a part of a circuit, and that is equal to the current times the resistance. And Ohm's law doesn't work for all materials. We're going to use it for the most part and assume for the most part it does work in the circuits we're working with. If the resistance of a material is not constant over the various currents and voltages we subject it to, then it's called a non-ohmic circuit, or it's a non-ohmic resistor. And if we were to graph these quantities, then we would not get a linear relationship. The circuit building simulation that you see here is one that you have access to. It looks like this. So this allows you to build a circuit of a variety of shapes. So you need a power supply, you need wires, so what we have here is a circuit. If we close the switch, then we have electrons running through the circuit. The light bulb goes on. We open the switch and it stops. So you can build a variety of different circuits with a variety of levels of complexity. It would probably be good to work with this in addition to the actual circuit that we build in the classroom, so you have practice setting them up and then drawing them. So what happens if you become part of the circuit? How does current affect your body, and why is current so dangerous? So if we look at this first cartoon, we've got someone that is not thinking clearly, making themselves part of the circuit. So some things that you should know: the amount of voltage in a standard household outlet, that would be 120 volts. What does voltage do? This should be reviewed from last unit. Voltage supplies the potential to the charge, and so the charge can transfer that energy. What does current actually do to your body? Well, current is a flow of charge carrying a large amount of energy, and so that energy is going to get transferred to your body as the current is going through it. What this does is it disrupts your nerve transmissions, and if the energy is high enough, it can burn or heat up the tissue to the point where it burns or cooks. Not a good thing. So in the next cartoon, our friend here is actually correct in terms of talking about the amount of resistance that your body has, whether it's dry skin or whether your skin is damp because you're nice and sweaty. Okay, how does a current affect the body? Well, a small amount, 1 milliamp, which is 0.001 amps, you can feel that. It may feel like tingling. If we increase it 5 times more current, so 5 milliamps, this is when it starts to hurt. If you've ever tangled with an electric fence, these usually carry somewhere between 1 and 5 milliamps, unless you've got really big animals or cows, in which case it might be a little bit higher than 5 milliamps. 3 times that, so 15 milliamps. What happens is, because it affects your nervous transmission, it starts to affect your voluntary muscle control, and your muscles will spasm. A current as small as 70 milliamps or 0.07 amps. If it happens to travel across your heart, it can be fatal, because what it'll do is it will disrupt the electrical transmissions in your heart and it can stop it. So if it happens for longer than a second, it can shut that down, stops your heart, and that's not a good thing. Your body's resistance to electrical current depends on the conditions that your body's in. If your skin is nice and dry, say on a day like today where the temperature is low, the humidity is low, the average resistance for your skin is about 5 times 10 to the 5th ohms. That's a high resistance, and if you remember back to Ohm's law, if I have a very high resistance for a given amount of voltage, that means there's a very tiny amount of current that's going to pass through you as part of the circuit. However, if you are wet, either you've just hopped out of a swimming pool, or you're still in a swimming pool, or the ocean, or a lake perhaps, or you're sweaty because you've been working out, or it's hot and it's summer, your resistance along the surface of your skin can drop down to about 100 ohms. So that same voltage that you might be connected to is going to do a lot more damage, because a lot more current will be able to travel through you as part of the circuit if your body's resistance is much lower. When you touch 120 volt wall outlet, there's 120 volts potential difference between you and the ground. So the electrons will travel through you. You primarily are at the potential. So you're at 120 volts, the electrons are going to travel through you. And if you're wearing shoes, that's what's insulated from the ground. So the electrons are going to jump through your shoes to try and get to the ground. Chances are that you might feel something. Okay, if this happens, or if you happen to get struck by lightning because you're outside and not paying attention, what happens is the electric shock, the electric energy, overheats your body tissues, burns them, and also disrupts the nervous functions. Okay, let's take a look at how much current you would be subjected to if you manage to connect with the 12-volt car battery terminals when you're trying to jump start a car. Happens in the winter, so your hands are dry, so your resistance is going to be 10 to the 5th, or about 100,000 ohms. So we have a 12-volt car battery. We want to find out how much current we experience. So what I find is I'm subjected to a current of 1.2 times 10 to the negative 4 amps. That's a pretty small current. That's about 0.12 milliamps. So we might feel something, but it's certainly not life-threatening. However, in the summer when we're working on the car, wanting to change out the battery perhaps, and our hands happen to be nice and sweaty, how much current are we subjected to this time? Same 12-volt battery. This time we're subjected to 0.12 amps. If we remember the list from before, 0.12 amps is pretty high, and so that is not good. Could be life-threatening, not something that you want to experience. Okay, in the next podcast we'll take a look at how power is associated with current and voltage and resistance.